Welcome back, everybody. Today we're going to be continuing to think about line integrals. We're going to introduce a helpful mnemonic, a little catchphrase that we can use to help show us how to translate a line integral once we've parameterized it. And second, we're going to look at another flavor of line integrals, a little bit different in what they're computing from the kind of standard line integrals that we introduced last time. But so real quick, let's recall the basic idea of these line integrals that we introduced last time. And so to start, we have some one-dimensional thing, a curve that we have some information about for each point along the curve. Right at each point, in this case x, y, z, we have some information, a function value, and we can stand up a stick with that height. And if we do that for every single point on this curve, we create a ribbon that's attached to our curve. And what this line integral over our curve is looking to compute is the net area of this ribbon once we've taken our curve and kind of laid it out flat. All right, and the way that we can compute these is, first of all, right, we need to get a parameterization of our curve. So we need to parameterize our curve C with some vector function R. And once we have that parameterization of our curve, we can use that to translate our integral in terms of that parameterization. Right, and here is the formula that we saw last time. Right, our limits of integration come from our starting and stopping values for t in our parameterization. And here, this notation here is just telling us to whatever x, y, and z are in terms of our parameterization, we're going to take those and plug them in for wherever we saw an x, y, or z in our original function. Then over here on the right, this ds becomes the size of the derivative of our parameterization dt. And that is our formula for how to translate a line integral in terms of a parameterization. And so to start, let's look at this helpful mnemonic, this catchphrase that we can use once we're staring at something like this, just a line integral on the left, and we're wondering how to translate it in terms of a parameterization. All right, the question here is, well, how do I translate a line integral in terms of a parameterization? And the mnemonic, the helpful catchphrase, is right here. Multiply by 1 over dt, dt. It's a very catchy catchphrase. I think that we can all agree to that. And this is the mnemonic that I'm talking about. What I want to do is show us how this works, how this kind of shows us what our line integral is going to translate to. So the way it works is, once we're staring at a line integral in its kind of raw form, and we're wondering how do we translate this, well, we say, multiply by 1 over dt, dt. And the idea is that this 1 over dt, that over dt is going to slide underneath our ds. And what we're staring at now is our function times ds dt, dt. And this, I claim, is showing us what our line integral translates to. So the idea here, we have to do some subbing, right? Our stop and start values for t plug in. Here's our start value and our stop value. Our function, right? We need to sub in what x, y, and z are in terms of our parameterization. But this ds dt, I claim, is telling us what should go there. And the idea here is that S, this is representing arc length along our curve, or in other words, distance. And so ds dt, well, that's the rate of change of distance. And thinking physically, well, what's the rate of change of distance? It's speed. And if you said velocity, that would be the rate of change of position, right, where positive and negative is taken into account. But the rate of change of just distance is speed. And well, what is speed? It's the size of velocity, right? And so that's showing us, this ds dt, that needs to get replaced with what it equals, the size of the velocity of our parameterization. And so it's in this way that a mnemonic shows us how our line integral translates. And what's nice is that as we introduce various kinds of line integrals, the mnemonic works for each and every one of them. So this is a really nice catchphrase to keep in mind as we go forward and work with these line integrals. Let's say it together. Multiply by 1 over dt dt. Very nice. All right, let's look at an example and practice putting this to work. Okay, so here, let's compute a line integral where this is our function, this is our information that we have at each point along our curve. And in this case, our curve is this line segment between these 2 points. I haven't tried to graph this very accurately, just from negative 150 up to 164. And so as always with any line integral, we have 2 steps. We want to parameterize our curve with some vector function. And once we have that, we can use our mnemonic to help us translate our integral. And so here, this line segment, our curve, right, this is part of a line. And parameterizing lines is something that we've actually been doing all the way since chapter 12. And so I want to give you a couple minutes. See if you can remember how we parameterized lines and try and get a parameterization of this line segment. And once you have that, translate our line integral and see what you can do to compute it. Why don't you pause the video and take some time and work through that. All right, well, let's talk through this. Recall how we went about parameterizing lines back in the day. Was we needed 2 pieces of information. Right, we needed a starting point, and here we have a couple. I'll just choose this one at the bottom. And we need a direction vector. And here we can get one just by stretching a vector from one point to the other. Right, and this is what we called our vector v. And once we had our point and our direction vector, well, we can get everything on the line just by starting at our base point here. Right, we called this p naught. And just adding scalings of our direction vector v. Right, and algebraically, it looked like this. Right, our vector function was our base point written as a vector plus scalings of our direction vector. Right, so here I've just kind of plugged in. We have our base point written as a vector. To stretch a vector from one point to the other, we subtract their coordinates. And so what we end up with for v is 214. And thinking ahead, in order to translate our line integral, we want to know what our x, y, and z components are for our parameterization. And so here, let's actually work this out, distribute the t, add the 2 vectors. This is what we're left with. The only question now is, what values of t are going to start us where we want to start and stop us where we want to stop. And here, well, since one of these points is the base point, if we want to start at our base point, well, we just don't want to scale by v at all. And so starting at 0 will start us at our base point here. And then in order to get to our second point, we just want to stretch all the way by 1v. And so we just want to make our t equal to 1. That should get us all the way to our second point. That's kind of a geometric way to see how to get those t's. We could also just you could double check by plugging in the 0 and plugging in the 1 here in order to see that those will indeed start us and stop us at the points that we want. All right, now that we have our parameterization, we want to go ahead and use it to translate our integral. And so, in order to translate our line integral, we use the mnemonic, right? And it says we want to multiply by 1 over dt dt. All right, and this is now exactly what we need to just fill in each part for, right? This function we had, we just need to plug in for x and z what x, y, and z are in terms of our parameterization. Right, here's our x, here's our y, which we actually don't see, so we won't need, but there's our z. And then after that, we have the rate of change of distance, which is speed, so we'll need to figure that out to completely translate this. And so here we plugged in our limits for t, 0 to 1. Here we plopped in what our x was. Over here we plopped in what z is in terms of our parameterization. And then over here, we need to find the size of the derivative of our parameterization. So over here, looking up at r hat, taking the derivative with respect to t, it's going to give us nice, clean, constant components, 2, 1, and 4. And so to take the size there, we just use our generalized Pythagorean theorem, 2 squared plus 1 squared plus 4 squared, and that boils down to root 21. And that's exactly what gets put in where it should go from our translation formula. At this point, our integral is completely set up in terms of t. We just need to do a little simplifying and work this out. We can take this root 21, it's just a constant multiple. We can slide that all the way out front if we want. Distribute the squared, becomes 16t squared. And at this point, we can just go ahead, crank through the antiderivatives, and evaluate from 0 to 1. And what we'll end up with is what's right here. And so here, again, the geometric interpretation here is that this number, about negative 24-ish, this is the net area of the ribbon that is formed on our curve here using our information from our function. And so the fact that we got a negative is just telling us that somehow primarily our information is negative along this line segment. All right, so that's how it can look to make use of our mnemonic to help us translate one of our standard line integrals. I want to introduce another related kind of line integral related to our standard line integral, but computing something slightly different. I like to call these projected line integrals. And so the idea, how you can tell that you're working with a projected line integral as opposed to a standard line integral is that after the d, we see just one of our variables, x, y, or z, instead of our ds, right, d, the arc length. And so our standard line integral, right, if we have a curve here that's in the xy plane, right, and we have at each point some function information, we can stand it up, we get some ribbon. Our standard line integral is computing the net area of this ribbon. Now these projected line integrals take this ribbon and somehow look at the shadow that it casts. If we project it, say, onto, in this case for dx, onto the x-axis. If you can imagine standing over here and shining a flashlight on our ribbon, this would be the shadow that it casts. And we're more or less computing the net area of this shadow, of this projection of our ribbon with this line integral with dx. And I say more or less because there's a little bit of a subtlety here. As we move along our curve, let's say we're moving, say, in this direction. As we move along our curve with this picture, we're always moving in the positive x direction. And when that's the case, our positive area is counted positively and negative area is counted negatively. But if somehow our curve did something funny and kind of changed course and was moving in the negative x direction, then things would flip and the positive kind of area would actually be counted negatively and subtracted. This isn't a big issue that we're going to be emphasizing a whole lot moving forward. I just want to bring this up. For example, this would come up if we projected this ribbon onto the y-axis. As we moved along our curve, sometimes we're moving in the positive y-axis, but other times we're moving in the negative y direction. And so here, the kind of shadow we'd see would have a little bit of adding, a little bit of subtracting going on with the shadow. So it's kind of a subtle geometric point. We're not going to think about it too much, but I wanted to bring it up. This is really the picture I'd like us to have in mind, that these projected line intervals are computing more or less the net area of the shadows of our ribbons. And what's great is that these line integrals, we can compute them all, we can translate them all using our mnemonic. So for example, if we were computing this line integral here, dz, and we were wondering how to translate it, we'd use our mnemonic and multiply by 1 over dt. And right there would be exactly how we would compute this line integral. Where here, dz dt, this would mean literally the derivative of the z component of our parametrization. And similarly, up here we have dy dt and dx dt. Those would be the derivatives of the y component and the x component. All right. Again, our mnemonic shows us the formula that we need to fill in. And so let's look at an example of how that can go just using the exact same function and curve that we were thinking about a moment ago. Here again, we're looking at adding up the same function information along our curve, the line segment from -150 to 164. And here we can use our exact same parametrization as we had initially. Here I'm just kind of copying, pasting from our work before. And then for step 2, in order to translate this line integral, which notice is indeed different than our standard line integral, right? The line integral that we computed before was ds. Here, dx means that we're computing a projected line integral. Right, but this line integral, in order to translate it, we just use the mnemonic and essentially follow the instructions. All right, so the mnemonic says multiply by 1 over dt. And then what we see here is exactly the form that our kind of translation needs to take. Right, we still have our function here. We need to plug in x, y if it was there, and z in terms of x, y, and z from our parameterization. And then here, what goes multiplied against that, dx dt, again, this is the derivative of just the x component of our parameterization. Right, and so looking up here, the x component of our parameterization is right here. The derivative of the x component is just the constant 2, and so that's what gets plopped in where it needs to go, replacing the dx dt with what it equals. At this point, computing this integral follows very much the same route as our standard line integral that we computed last time. We can take this 2, pull it out front. We're going to get the same antiderivative as before, just with a different constant out front. And this is what we get as our final answer if you want to work through the details there. So that's how it can look to compute a projected line integral. Again, as long as we can remember the mnemonic, that will show us exactly how our line integral translates and how to compute it once we've parameterized our curve. Now to finish up today, I want to introduce just a little bit of notational shorthand that gets used for these projected line integrals, specifically if we are adding up more than one of them together. Let's say that we had some curve C. I don't know, maybe it looks like this. Whee! There it is. There's our C. And we have some function information f and some function information g, and we're computing these projected line integrals and adding them up. As a shorthand, since we're using the same curve, we take these integrals and kind of just pull them out to the left, and we just write it once. So we would write this as integral over c of f dx plus g dz. And what's nice is that even this kind of notational shorthand way of writing this line integral, it works beautifully with our mnemonic. All right, so once again, the mnemonic shows us how this translates. And let me just kind of show us how that looks. This is just a real quick how this looks to use our mnemonic here. Right, the mnemonic is to multiply by 1 over dt, and we're multiplying this whole thing by that. And so here, this over dt is actually going to distribute to both the dz and the dx. And so we'll get dx dt over here against the f, and dz dt against the g. And so here, this is showing us exactly how this line integral translates. We need to make our substitutions for the variables in f and g, plop in the derivative of the x components of our parameterization here, the derivative of the z components here, and and we include our starting and stopping values for parameterization. All right, and once we've done all that, we've correctly translated this line integral. All right, and this would also go through in a very similar way if one of these was dy or we had all three of them. The mnemonic shows us how this translates. All right, well, that's it for today. Good work, everybody. We'll play around with line integrals some more tomorrow. Until then, if you have any questions, post them to Piazza, and I'll see you next time.